apologies to you for the minute we have been wasted trying to configure here soon. Hello everyone. I'm gonna talk about a methodology we have been developing for the determination of contrast agent relaxivity using magnetic resonance imaging. As you may be aware, MRI is one of the most powerful imaging techniques. It has several advantages like non-invasive, high spatial resolution, and high contrast between soft tissues, and the ability to extract quantitative information about dynamic processes. However, it has one of the biggest disadvantages is its relatively low sensitivity, which can be one of the ways in which it can be overcome is by the use of exogenous contrast agents. The efficiency of these contrast agents is characterized by the relaxivity. If you have a high relaxivity, it means you have a greatest contrast enhancement in your image at a lower dose. Relaxivity depends on several factors, the field strength of your MRI machine, the correlation times on the magnetic interactions, and the temperature. It can be determined by calculating the effect that the contrast agent has on the observed relaxation rate. Traditionally, this determination has been done using NMR relaxometer, but now there is an increasing trend to use the clinical MRI scanner because you're characterizing your contrast agent under the same experimental conditions it will be used. The first thing we need to take into account is to use when performing the experiment to have alongside the CA samples you want to characterize solutions at different concentrations with known T1, T2 values. This concentration range for the solutions must be such that the T1 and T2 values are measurable by your clinical MRI scanner. If you have a very high concentration, it might recover too fast and you won't be able to see it on your image. We have been using the two type of pulse sequences, the spin echo sequence, in which this is the expression from a spin echo sequence, everybody knows it. In order to perform our T1 estimation, we set the echo time to the minimum of your scanner, and we sample the magnetization along its recovery path. And in the case of a T2 estimation, we set the repetition time to the at least more or equal to 5 times the T1 of the largest sample in the image, and we sample along for different echo times. In the case of the spin echo, the inversion recovery spin echo sequence, the expression goes like this. In order to perform a T1 estimation, we set the TR once again to 5 times the largest T1 in the sample and the echo time to the minimum. And you sample the magnetization from along this recovery path for different inversion times. One of the parameters that is introduced to take into account is the parameter A here, to take into account the RF imperfections. These imperfections can be mapped with different methods. When the one we're using is the dual angle method, in which you acquire 2 different images with flip angle related of this condition. From using the ratio of these 2 images, you can estimate what is the true flip angle distribution you have. Other experimental things you need to take into account is your signal-to-noise ratio, because the variance in your relaxation time estimates depends inversely on your signal-to-noise ratio. The higher the signal-to-noise ratio, the less variance you have in your T1 estimation. To estimate the SNR, you can do some measurements on the phantom of the samples and on the background. Also, you need to take into account the susceptibility effects when you're doing this kind of measurement. You must select the ROIs from the TA samples away from its boundaries where partial volume and susceptibility effects are accentuated. And in order to minimize the influence of one sample onto its neighbors, you need to separate it at least one diameter. And another thing to take into account is the temperature, which must be controlled throughout the duration of your experiment, because as we saw previously, the relaxivity depends on the temperature. Well, this is the general methodology overview. Now we've been seeing how to prepare the sample, the SNR-RF assessment, and once you select your pulse sequence, whether it is spin echo or inversion recovery, we run into the automatic software processing part, in which we are going to estimate your T1 or T2 relaxation times using the Levenberg-Markov algorithm. And then you move on to proceed, knowing the concentration you have in the sample you want to characterize to estimate the relaxivity by linear regression. So this is the tool we have developed, has several steps in order to measure the relaxivity. First, you handle its input with DICOM files. Once you get your DICOM file, you can choose to perform automatic noise segmentation and row installation, or you can do it manually if you want. We calculate the mean and standard deviation from each ROI for the different time points, mean the echo time, repetition time, or inversion times. And we estimate the relaxation time using a 3-parameter model with the equation we previously saw using the Levenberg-Markov algorithm, which is a very robust algorithm for nonlinear least square curve fitting. And this is the objective function. This is the signal we measure in each ROI. This is the different echo time, inversion time, or repetition time, and beta is a parameter vector which consists of 3 different parameters: your relaxation times, your signal baseline, and the parameter A we saw previously. And when you determine the relaxation times, it is easy to obtain the relaxivity by linear fitting of this equation. This is the general overview of the protocol we have been working on. Here you can see in this window, in this axis, you can scroll through the images of the different samples. You can select your kind of detection scheme you want. If you want the software to do it automatically, or you do it manually by clicking a point and selecting the ROI on the image. This is the DICOM header information, in which you can see all the parameters of the sequence. This is an access to track the evolution of each sample along in this case it was an spin echo sequence, along for the different repetition times you have. This is the minimum TR, especially in our scanner, which allows you to check that if you have a sample which T1 is less than this, you won't be able to measure it. So once you estimate your relaxation times, you move on to fit with the relaxivity by clicking here. As a matter of conclusions, we can say that we developed a methodology to estimate the relaxivity of contrast agent solution using clinical MRI, taking into account the several sources of error and its compensations. The automatic toolbox greatly increased the speed of the determination of the relaxivity by doing everything automatically, so you can guarantee the reproducibility of the results. And the methodology helps to reduce the measurement time and uncertainty in the results. So thank you.